Welcome back to the Deep Dive, where we unpack complex topics and give you the core knowledge you need. Today, we are jumping into the very engine room of progress, technology, research, and development, R&D.
That's right.
I mean, this is really the foundation, isn't it? It's where every single modern innovation in engineering and geoscience actually comes from.
It absolutely is. And our mission today is to, unpack its essential parts, look at that whole cycle of innovation, and maybe most importantly, see why it's so central to professional responsibility.
How theory becomes reality.
Exactly.
And this is just critical information, whether you're working on a project or, and this is a big one, if you're preparing for the Canadian NPPE exam, understanding R&D is, well, it's fundamental. And on that note, if you are preparing for that professional future, go ahead and subscribe now. We're building the knowledge base you need for the NPPE, and you really don't want to miss a single one of these deep dives. Okay, so let's get into it. We hear the term R&D all the time, but it's really two complementary processes, isn't it?
That's the key. It starts with research. And that's just the systematic investigation to discover new knowledge.
Pure exploration.
In a way, yeah. And even that breaks down into two types. You've got basic research, which is all about fundamental understanding. No immediate commercial goal.
So like studying rock formations just to understand them better?
Precisely, just to understand tectonic stress. And then you have applied research, which is aimed at solving a very specific practical problem.
Like finding a way to get a certain pollutant out of a water source.
Exactly that. A perfect example.
Okay, so research gives you the knowledge. The second pillar has to be about using that knowledge.
And that's development. This is where you transform that knowledge into something tangible, a new material, a new device, a new process.
And the professional, the engineer, or geoscientist, they're the bridge between those two worlds.
They are the bridge. They take that theoretical insight and turn it into something real, something deployable.
This is where it gets really interesting for me, the R&D cycle. It's not linear. It's continuous.
Oh, it's a loop, for sure. It typically starts with phase 1, problem identification. You have to recognize a need first.
You can't solve a problem you don't know you have.
Right. From there, you move into the research phase, generating data, gathering insights. Then comes step 3, the development phase, which is all about design and prototyping.
And I'm guessing this is where the costs start to go way, way up.
They explode, which leads right into step 4, testing and validation. This part is critical. It's expensive, and frankly, it's where most new ideas fail.
So this is the pilot project stage.
Yes, you have to rigorously verify performance, reliability, safety. You just can't skip this, especially when public safety is on the line.
And if it gets through all that?
Then you hit step 5, commercialization or implementation. You bring the technology into widespread use. And of course, that often uncovers new problems.
Then a whole cycle starts all over again.
And the cycle restarts.
That makes so much sense. So R&D isn't just a lab activity, it shapes entire economies. What are its big picture roles?
Well, it has 3 massive impacts. First, and most obviously, it's the engine driving innovation. Without it, we just stagnate.
You can see that in so many Canadian examples.
Totally. Look at the development of steam-assisted gravity drainage, Sandy D for the oil sands, or lightweight composites for the aerospace industry. That's all the direct result of R&D.
And those innovations, those technical wins, they feed directly into the second role, which is about the economy.
Right. Enhancing economic competitiveness. I mean, countries that are strong in R&D, they lead globally. For Canada, it helps diversify the economy away from just resource extraction.
So it's about creating new, high-value industries.
Exactly. Clean tech, advanced manufacturing, that kind of thing. Strong R&D attracts global investment. It's a huge signal.
And the third role. This one seems to tie right back into a professional's core duties.
It does. It's about supporting sustainability. This is the critical link to protecting public welfare.
So developing things like renewable energy systems or carbon capture.
Yes, or pioneering new clean water systems for remote communities. This is where we balance progress with our environmental and social duties. It's a core ethical responsibility.
Okay, let's go back to the types of research for a second. We mentioned basic and applied, but there's the third category, right?
Yes, experimental development. But it's helpful to think of them all on a spectrum. Basic research is that blue sky thinking.
The long game.
The very long game. Results might take decades, but the foundational knowledge you get is priceless.
So if basic is about discovery for its own sake, where does applied research fit in?
Applied research, it has a deadline. It's focused on solving a specific, immediate problem. A great Canadian example would be developing a new corrosion-resistant alloy for a bridge that has to survive our winters.
With all the road salt.
With all the road salt, you have a defined problem and you need a solution, relatively quickly.
And then the rubber hits the road. Experimental development.
This is the prototype stage. This is where you convert those research findings into something that actually works. Think about the CanDU nuclear reactor.
A huge Canadian
A
achievement.
massive achievement. But that design didn't just appear. It took years of experimental development to prove that the heavy water technology could be scaled up safely and reliably. That whole process of testing and piloting, that's experimental development.
The CanDU project really shows how much collaboration is needed. Which brings us to the Canadian R&D ecosystem. It's not just one company in a lab, is it?
Not at all. It's a partnership, a kind of tripartite model between universities which focus on the fundamental research.
In training the next generation of professionals.
Of course. Then you have private industries, which are all about commercialization and getting things to market. And finally, government agencies.
They handle the funding and regulation side of things.
Funding, regulation, and setting standards. Yeah.
Can we name some of the key players? Those acronyms come up all the time.
We should. So you have NSCRC, the Natural Sciences and Engineering Research Council. They are absolutely vital because they fund so much of the university-level research. They're the foundation.
Okay, NSCRC.
Then there's the National Research Council, the NRC. They often act as that bridge, helping take research and scale it up for companies.
And we can't forget the Canadian Space Agency, the CSA.
Especially with our expertise in remote sensing. But for the private sector, maybe the biggest driver is the SR&ED program.
That's the tax incentive program.
Exactly. It's a huge tax incentive that encourages companies to take those big R&D risks right here in Canada.
That makes sense. So looking at where we are now, what's on the cutting edge? Where is this whole ecosystem putting its energy?
Well, the speed of change right now is incredible, and a lot of it is driven by computing power. Artificial intelligence and data science are just transforming engineering.
How so?
We're using it for predictive modeling to figure out how long infrastructure will last, to optimize resource extraction. It's everywhere.
And the other big one has to be green technology.
Oh, absolutely. It dominates the agenda. You have hydrogen fuel cells, advanced battery storage, carbon capture. All these are R&D efforts aimed at building a low-carbon economy.
Which brings us to a really crucial point. R&D involves high risk, and with things like AI or green energy, the public impact is enormous.
Yeah.
That puts a huge focus on professional responsibility.
It's paramount. It's non-negotiable for licensure.
So what are the cornerstones of ethical conduct here?
There are 4, really. The first is integrity. You have to report your results honestly, no fabricating data. The scientific record has to be trustworthy.
Okay, integrity first.
Second, and this is so important for engineers and geoscientists, is accountability. You must prioritize public welfare and safety at every single stage.
Every experiment, every deployment.
Every single one. Then there's transparency. You have to disclose your funding sources, any potential conflicts of interest. It's about building and maintaining public trust.
And if someone fails on these points, say they misrepresent data.
The consequences are severe. Legal, financial, ethical. And it can absolutely lead to losing your professional license.
Which brings us to the 4th cornerstone.
Intellectual property respect. Avoiding plagiarism, respecting patents, protecting data. In a competitive R&D world, this is just vital.
And because the technology is moving so fast, that commitment to ethics has to be ongoing, right?
It has to be. Which leads directly to the need for lifelong learning and competence. Continuous professional development. Your knowledge has to stay current. It's an obligation, especially if you're working on the cutting edge.
Let's ground this with a few more of those case studies. We mentioned the CanDU reactor and SEG-D. What about from the geoscience side?
A fantastic example is Arctic climate monitoring. Years of focused R&D using remote sensing and field work give us absolutely critical data on permafrost thaw.
And that's not just for academic papers.
No, not at all. It directly guides national policy. It helps us design safer infrastructure in the north. It fulfills our international climate science duties. It's a perfect blend of environmental and social impact.
So when we pull this all together, what does it mean for the professional listening to this?
It means that R&D is the highest expression of the professional mission. It's about serving humanity through innovation, through knowledge, and through unwavering ethical practice.
It sounds simple, but it's incredibly complex in practice.
Oh, it is. R&D faces huge challenges, the costs, the patent issues, and now these massive new ethical dilemmas.
Like what?
like trying to balance the speed of innovation with proper regulation, or dealing with the social impact of automation, of AI displacing jobs. These are not easy questions.
Which leaves us with a really important final thought for you, our listener, as you look at your own career. How do we make sure our ethical frameworks or professional standards evolve as fast as the technology they're supposed to govern?
That is the challenge, and it requires leadership from every single professional. Thank you for joining us for this deep dive.
And if you found this discussion valuable and you are preparing for your professional future, subscribe now to our deep dives. It's the knowledge you need to be successful on the NPPE exam and throughout your entire career. We'll see you next time.